This is an update in my CPU design project. Now in the top level here, I've now got 6 general purpose registers, so they now run from R0 to R5, where previously we only had 4. Now we also had a register here which was originally dedicated as a link register, but at the moment we don't really need that, and potentially moving forward we won't need it. So I've changed this into an index register, and we're going to use this in order to generate some interesting addressing modes. So that's the only difference really in the top level here. Everything else that we've changed is down in the control section, and there's not an awful lot of change, but I'll explain this to you here. So we have our 16-bit instruction, and what I've done is I've taken the opcode here, which is 6 bits, and I've moved it to the most significant position. We also have our reg A here, which is these 4 bits, and our reg B, which is the least significant 4 bits, and it left the 2 bits here free. Now I'm going to use these 2 bits in order to choose addressing modes. Now don't worry if you're unsure about addressing modes, I will go through a full video or several videos on addressing modes in the final course. But I'll take these 2 bits here, and these 2 bits are going to go into the microcoded control unit, and they're going to pass into this multiplexer, and the multiplexer is just going to choose 4 values. So what we're going to do with the addressing mode is we're going to have 16 possible instructions using one addressing mode, 16 possible instructions using the second, and then the third, and then the fourth. So we can have up to 64 instructions, and we're going to be able to have a maximum of 16 in each instruction mode. In each addressing mode. So all we're going to do is split this microcoded little compression ROM into 4 little blocks, each from 0 to 16, or sorry, 1 to 16 or 0 to 15. So for example, if we were going to use say immediate addressing, then we would ensure that our immediate addressing lives in the first 16 bits here. So these first 16 bits are going to give us the position within the ROM. And then if we were to move on to another addressing mode, then the second addressing mode would occur for the next 16 bits. And then we could get the next 16 bits with the third addressing mode, and then the final 16 bits with the fourth addressing mode, and you can see that here. So if we had an opcode for 0, all zeros here, and it's choosing this first position here, and then we decided we're going to move up on to another addressing mode, then we make this a 1, and then it would take this value here and it would add it on to this value here. So we're really adding 16 on, and it would jump to the next block of instructions, and that next block would cover the next set of addressing modes. And we can do the same for this one here, and also the final addressing mode here. So it's a neat and simple little way of splitting our microcoded ROM into 4 separate blocks, which cover 4 separate addressing modes, each with 16 possible instructions. So that's really where I am at the moment. Now, it means that what I have to do is I'll have to go through and first of all choose the addressing modes I'm interested in keeping, because I would much prefer to have say 3 spare pins and then be able to choose 8 addressing modes. but I've only got 2, so it does allow us to choose 4. So it is only a small CPU, and 4 should be enough for us to provide enough functionality so that whenever we go further up in the abstraction layer up towards a compiler, it'll give us enough options to compile a code down into assembly language. And our 64 instructions over 4 addressing modes should be enough. So I'll show you as well just a couple other things that I covered in the Excel spreadsheet here. Now I'll make this a little bit bigger. So I added in a few extra commands. I'll take my image off here so you can see this properly. Okay, so I've added in, we've got our load and our store, our data, our jump, register address, and so on and so forth. And we have got our jump to subroutine and our return, and our push and our pop, and we have our ALU instructions, and we've got our decrement increment. We've got this one down here which is move R, so this is moving between registers, and we've also got this one move M, so this moves between memory locations. We've got this here which is an exchange R, so this doesn't just move, it actually swaps over 2 register values. So I'll bring my image back up here and shuffle over here. There we go. So this will allow us to swap the positions of registers, so they just swap over. And I've also got here a load I, so this was my first foray into the addressing modes, and this is going to load I means index, so this allows us to load a value from memory into a register. But it doesn't just pick the memory location, it picks the memory location and then adds on an index value, and it gets the index value from the index register. So it goes to the memory location and then adds on a value for an index. It picks that position, that information within that block of our memory, takes it out and puts it back into a register of our choice. So that was the first one I did, but obviously the way that the design has been made here, all of these different instructions, they're just a mixture. They're a mixture of immediate mode and indirect addressing modes. So they're all kind of mixed up at the moment. So what I have to do is unravel them and then choose the ones I want to keep and then create the addressing modes for each of those. So that's what I will do over the next day or so. But as it stands now, we've still got quite a robust control unit, and it's quite a general control unit, and it does allow us to work through here. For example, if I wanted to do a load, or let's say a load instruction, so the load instruction, we would have our source, would be RA and RB, but RA and RB can be any one of our registers, and RB can be any one of our registers. So it's really a nice kind of general control unit. Now, this isn't the only thing I've done so far. I've also taken the floating point adder and subtractor and the multiplier, which are 32-bit designs, and I've ported them over into Logisim Evolution from the original Logisim, and I've also created 16-bit versions of them, because whenever I put the floating point unit, I might just put the 16-bit in as opposed to having the 32-bit. We could keep the 32-bit floating point unit, but it would mean that we would have to transfer 16 bits of data at a time into the floating point unit and transfer the 16 bits out. And also 16 bits for a floating point unit, it's going to be enough to show the CPU working, and it's going to be enough for us to create some, hopefully create some kind of graphical simulations. So that's where I'm at the moment, and I'll be over the rest of this week. We'll be choosing the addressing modes and updating the microcoded ROM with those new addressing modes, and also trying to get the adder, subtractor, multiplier ported into the design. So whenever I put that into the design, I will probably put it in at this level here. So I'm going to put it in effect as an input-output device. So it's kind of like having a CPU and then having a separate floating point unit as a separate chip. The way that was, say, in the mid-early 1980s, when you had a CPU and then like a math coprocessor. And the math coprocessor is really just a floating point unit with some nice little bit of mathematical formulas in it. So that's where I am at the moment, and I'll get cracking on with this, and I'll give you a shout whenever I've got any other updates. So thank you for listening. I'll get you in the next video. Goodbye.